portions. Of course, from rainfall to runoff, they have like a flow loss, the rainfall loss, this infiltration, basic infiltration. For the ICS, of course, we have an approach how to calculate the infiltration to the ground. That's called loss. Then after loss, how the runoff becomes the peak discharge. Yeah, that's what we're talking about right today. So basically, when we talk about hydrology, we look at the rainfalls, right? Rainfall is pretty easy now. The NOAA, they have a website. We can take out any point of the rainfalls based on the website. They have the different some frequencies, and pretty easy. So after rainfall, we need to know how to the distributions, because the rainfall within like the because the basically the rainfall with have like different time, they have the rainfall depths, right? This is called distributions. Basically, we now all the design we're looking for the 24 hours for the Maryland or the or East Coast area. That area is the type, basically called a type 2. This curve is the 24 hours like this. So this is the green. So we use the type 2, but in Maryland, I think this just the NOAA type C. Maryland have a study based on the NOAA distributions. They found out that the little bit different distribution from the type 2. That's why some counties and state accept the NOAA type C distribution. This distribution basically the have a little bit different, but not much. But now we use the NOAA type C. That's all the software built in the distributions. So the second one, the first one rainfall, then distribution, then we need like a CN, that's a loss. So basically we have like a land use type, course type. So from this and the hydraulic conditions, I don't think most of people maybe not pay attention to the hydraulic condition. Basically we have three types, the ARC 1, 2, 3. 1 is dry and 2 is normal and 3 is wet, right? EMC2 is the normal condition is the mostly we use. That's the CN. If you look at the land use type and the CN number, they call hydraulic conditions. Use they point out the EMC2. But of course they have like NRCS, they have a standard tables how to convert 2 to 3 for each of the CN numbers. So we don't need to talk about it because we focus on MIC2 CN numbers. So how do you calculate loss? That's pretty simple. We get the different based on the land use, the cover type and the soil type. We come out CN numbers. The CN number, the calculate the potential retention. This is just like science numbers, but this is just a calculation approach. Then you come out RE pointed to S. This is called initial abstraction, whatever you call it, it's a loss. Then based on this, you get if you look at different storm frequency, like 1 year, 2 year, 10 years. For example, 10 years you get a P, right? Then RA the ratio you get it, right? Then the TC, of course, the watershed you can get a TC sheet flow, shallow flow, concentrated flow, and channel flow. You get a TC is pretty, because most of people already know, we don't need to talk about it in details. So get a TC, then you come out QU, they just called a unit discharge. What means unit discharge? Unit is cubic feet per second per square mile per inch. assume that the 1 inch water on the ground, then 1 square miles, then what that should be the flows. That's called the units peak flows. After that, we how to get this one, because these are different locations have different QU, right? But we have the equation. Most of people, they use the fingers. They use like a chart. For example, TR55, they have a chart with the different REP ratios. You get a QU based on TC, and you get QU. But actually, they have equations. So of course, the different the C0, these are coefficients. These come from the IRP numbers, I over P number ratios. Different ratio have different C numbers. Of course, this equation, the C, of course, rely on the distribution. Basically, if we distribute distribution two type 2, these are equations, then you come out QU. Then after you come out QU, then you come out then you calculate the runoff. This runoff, basically, this just like calculate the depth. You don't worry about the you don't calculate the flow, but you calculate how much water after 20, for example, after 24 hours, how much old water accessed after infiltration. That's the Q. Then if you have that Q, then you come out the flow, the peak flows. It's the high unit. You have a square mile, whatever the area. Then the new they call the rainfall in depth. The factor doesn't matter, because we don't for the design, we don't consider much about the surface tension by the pond. So we basically use one. That's how the peak flow come from. Then you don't worry about this. Just like tell you how to calculate the peak flows. But now everything is built in the software. So for example, this is the TR55. For the TR55, you see what happens. This is like you need a type, whatever the state, you need the distribution input, and the unit hydrograph. We talk later, but you remember this. We use the unit hydrograph. Then you come out area and CN numbers, TC. The same thing. We the CN numbers, TC, and basically reinforce in the reinforce building, or you click here, you will see the different rainfall, right? So come out the peak flows. This pretty much like this hydrograph is flow with the time, right? For example, the peak, right? Then basically the TR50 file, of course they have now developed. Basically, if this is a small area, like for example, you look at the less than 150 acres, you can use it just pretty simple. But if a large area, TR55 may not suitable. You just you need to change it to TR20. And the same things, we need a rainfall distribution, as we talked, and the basic rainfall distribution and area, and of course the rain, the other stuff already distribution already built in. You don't need this. You don't need the worry about the units hydrograph already built in. So after you run the model, you also get like hydrograph, right? So this TR20, TR50, TR20 is now popular for the Maryland. So of course, now the HAC HMS, you know, this you know, as you know, for the you know, the US, the you know, the now if you do the hydrologic calculations, watershed studies, HAC HMS is I think is so far is the best you know, the software we can do, we can use. TR50, TR20, I think this is just like for the you know, for this for the, you know, the Maryland. But if you other state, maybe the HMS is more popular compared to the TR20. For example, Virginia, if you use the TR20, maybe somebody doesn't know what the TR20 is, right? So so I think, you know, now the Maryland already accept basically the HMS is pretty simple, not so complete. For example, this product, you know, I think that anchor beam, you know, the bridge 32 and 31 is TC Brown. I at the beginning I developed this one random mode, but you know, maybe I think maybe the you know, the states maybe not accept, but I just like change it to TR20. But basically what hold this is just a watershed and a reach, and you know, they come out the different you know, the location with the peak flows, like a bridge 33, 31. The input is the same. For example, here is just like we use like a loss curve numbers and use a SCS unit hydrograph. They come out different, you know, the peak flow with the different, you know, you know, different, you know, the watershed. So, you know, that's the HMS. Then okay, then so you with somebody like talked about you know, the SCS unit hydrograph. What it means? Basically, unit hydrograph, this little bit the develop process, you know, the complicated, but it's pretty simple. You just like simple with basically after, you know, the you know, they develop like when they develop, they assume the water on the ground, the in the 1-inch water depth, right? Then this 1-inch depth, they get like experiment, do some like lab tests, and they get like the outlet. They have like, you know, this curve basically. This curve not this just really depend, you know, you know, the lab test, and of course it tested by the watershed. But this is a shape, right? What happens, like, you know, the water, they have like they assume 1-inch depth waters and come out at outlet. For example, you know, the at outlet test the flow, that, you know, so they come out of this curve, the cubic feet per second at different times. They got the curve. This is called a unit curve. Then if the watershed get a unit curve, then if you want to see the like a P, like, you know, you know, rainfall, like maybe for example 10-inch, you just simply, you know, time time this curve, then come out a large curve. This you know, the hydrograph for the watershed. This is simple thinking. How to develop, but after that they try to, you know, you know, simple. That's why they develop out, you know, the utilities, basically utilities, unitilities, right? So the peak, you know, each of the Q divided by the peak flow. This is a peak flow, right? Divided by peak flow. Then the time divided by the TP. What's the TP? TP, time to peak. So then come out the unit list. that's called the unit hydrograph curve, right? Uh, Basically, these are like if you don't understand, it's fine because they are like little bit complex. This most of like based on the lab and the test verified by the watershed. Basically, their lag time. What the lag time is, the raw and sun they use 6.6 TC. This really based on this number really based on the field test. No, there's no any special reason there. So uh, you get lag time. Basically the critical thing is the TC. Of course, the calculate TC that you get a lag time, and the TC based on then come out the TC equal to 1.7 lag time. Then TP, what's the TP here is just like equations, right? D the delta T, like for example, you interval when you run the model, you see the like even the TR25, TR20, they have like a like 0.1, yeah, 0.1, 0.2, the calculation step. That's the D. So after that, of course the peak rate fraction. Of course this just like a normal condition. This is common conditions, right? So that's the they call the unit hydrograph. That's all the of course in the unit cross hydrograph, different approach they have a different. For example, you if you look at the clock, they have clock unit. You have other method like grain attempts. They have the different unit hydrograph. I can show you what the time. Okay, I still have time, right? Okay, HMS. So if we look at it, for example, you look at this, the watershed, like for example here, they have a area, if a low semester, you have a bunch of low semester, like what we use SCS and covered now, right? So they have like a different, you see the how much grand temp. I think the second popular one is the grand temp. Grand temp is just like use the infiltrations, soil infiltrations, hydraulic conductivities, the moist content, with the saturation, water content, this kind of thing. So, but the Maryland, I think they don't accept this one. But in the west area, like Arizona here, I think they use this one because it's a dry area. The infiltration basically loss based on the because the soil is dry, the saturation rate maybe very low, so it lost a lot. That's what this one. But the Maryland we use, for example, this unit hydrograph, they have like different, the clock unit, modified clock unit, sender, what they have bunch of the different ports have different units curve. What's the different? Different means the curve, for example, this is unitless, right? Unitless, the curve shape is a little bit different. But the ICS is the most ICS is the most popular one we use. So yeah, that's So yeah, they pretty much based on this, we the software use the software we can get the peak flows. This is then after we get the peak flow, we try to design, right? Use the peak flow for the design. Basically, that's what here is just like hydraulic study. We know how to design the culvert. So the basic the zero is simple. Just use the mining equations. Mining equation, I think most people familiar with is the critical, the parameter is iron values. The iron values they have like a pretty standard. For example, this not basically this this value for the pipe. For example, when we calculate the CMP pipe, we basically use a 0.0224. If you use it, we no one will doubt you because it is this the popular and common numbers for the CMPs. Whatever the CMP type is, like so for the the concrete and the RCP, we use the basic we use the the 0.013, right? Some people use a 0.012 if the cohort the large enough. But most of them we use we use a 0.013. That's why we can when we design we use the the map parameters and values, how to get it. This basically the tables. This comes from study of the true 1949. This you can if you have time you can read these papers. They come out the different things. But for us, we focus on the concrete and CMPs. That's yeah, of course. If that we sometime we sometimes we see the break, we see the break covered. It's a very old break covered. They have different the parameter you can look at if you design. These tables these tables come from the different standard. The AISI they test this, and the basically CMPs iron values change with the with the diameters and the type. But the basically that's why when we design for the design purpose we don't need to consider too much about the size. We just use a 0.024. That's common numbers. No, but if you look at the large pipe, for example, made 72, 78, this one like very huge, maybe you consider the different numbers. But for within our design, we don't need. So the most popular software is HY8. You tell you the sizing based on the peak flow to sizing the hydro sizing the pipes. So this HY8. We just like tell you how to design this. For example, this already has it. So, So you have like the name, right? Whatever the name, here you come out, the minimum design, the maximum. Minimum, this just like, for example, your design 10 years, the 10 years is like a 30 cubic meters a second, right? You can, yeah, the minimum you can like a 10 for whatever the number is. If once you below this number is fine, for example, you can minimum 10. Then maximum same things. Maximum you can maybe this a third 10 years you can 100 years, maybe for example 150, right? It doesn't matter. The design flow is what if you the input here number is we just try to found the exactly water head for the flows. That's why we consider design flows. We will show you later. So basically, this flows then come out till water did. Basically, we have like a trapezoid channel. The bottom, for example, for this when we call like a 3 foot. What the two this this doesn't matter. It really depend on the downstream channel, the dimension and geometry thing. For example, here we will get like for example the bottom length is 3 foot, side slope 3, and the channel slope for example like 0.1%. And the manual equation, yeah, the manual equations for the most of the channels, if you look at if you talking about the channel, the manual equations, the manual is in most like for the Maryland area, between 0.03 to 0.05. That's the range. If you see the in the Maryland, if you see somebody trying to design use like the channel use like 0.02, I think definitely that is not correct. If the user 0.03, I think okay, acceptable. If something like if you see the channel manual equation over 0.5 or 0.05, 0.06. I think that's not good. It's really not reasonable. So you remember the channel between the 0.03 to 0.05, around 0.4. If you use a 0.04 or 0.035 for the channels, nobody doubt you. I think you within a good range. So the channel inverse, for example, the channel inverse this channel inverse should be the same as the same as the the pipe inverse. Let me show. Then we assume like 300, for example. So the roadway if the pipe if the pipe overflow happened, you need to pay attention to this. You need to really the elevations. If you assume that no and overtopping happened, that doesn't matter. So this once you have like the elevation above the maximum water elevation, it should be okay. So the first station 0 and the crest length more we will get 20. This really depend on the roadway, right? Crest elevation, for example, we have like 20, 33, 20, maybe 315. Because we just assume, right? This is like inward here 300, we got 15 foot above highway. I think the rhythm. So paved top, no, this credit is too small, maybe 50. Then the top, for example, we have two lines channels, two line roadways, they are 24. So the culvert, the shape, I think most of them like use the circular. So the concrete, the diameter, their foot like maybe 24, 36-inch embedded? No. The manual you see here is the manual. If you use by default they use the 22, we use the 24, right? 20 no, they have used the like 0.013. 0.013. This is ICP typical values. So 5 street. Why is it called street? Because they have like let me snap. So basically, when we design, they of course this is this is a roadway, right? Then we have a cover here, the street cover like this, right? But some area, some some if it the upstream and downstream drop a lot. For example, they have some case like right, this upstream, this downstream. If that's a slope large, we what we can do, we can we could design a curved band like the banded curve portions here, and then banded the whole band there. Yeah, most cases, if this is shallow, we can use a manholes. But if this one is like very deep, we just like have like a vertical band, the pipe like the pipe like this. So this way the now HY8 they have like the functions. They call the bring back broken back. No, that's but we pay most likely we use the street. So here is this entrance loss, the carry the entrance loss called entrance loss. If we basically if we have a square, the head wall, square head wall, and section whatever, I think we use 0.5. If they don't have any head wall or it's just like project to the channel is more large. For example, maybe 0.7. But for our we basically have like for the culvert at least we have like the head wall or something, right? We most likely we use 0.5. Depression, we don't have any depression inlet depression. Basically, I think when we design the when we design the M14s, what happened, the drive very shallow, right? And this flow line, right? Then this is like, for example, this like they are 2 foot, but we need like a 24-inch pipe. So if we 24-inch, there's no one cover there. What so how we do that? We just like lower the pipe. This area, this area, this area, basically this is the infective area. The water, the water goes through this, and this is called the embed. For the large culvert, like for large culvert, for example, we design like a box culvert. This is this is cross section. So this stream. Then we want to bury this for what, for the fish pass, for the fish, like, because they have like a face protection, law or something. They don't want the fish go through the concrete things. So they lower, lower. For example, this like a the 8-foot box covered, but the embed 1 foot, and the bed 1 foot. Then the bottom is like a natural channels. When we design like then the water, then the fish can go through, like there no any change of water, the bottom, soil type, whatever, the bed, the stream bed. That's why sometimes they use the embedded. But for example, if you embedded here, they call the depression. Depression. For example, for this one we for 0.5, right? And the press slope is the same, and the crest it really doesn't matter. We embed the whole the whole area, the whole length things. So that's come out this. For the most of this just for the large culvert and large stream, but for this one we don't. So just to show how to input this, what it means for the culvert itself, like for the in starting 0, inlet elevation, for example, 0.1. And the outlet station, we assume the pipe length is 100, and offset elevations, outer elevation is the same as this one, is 300, and number of barrels is 1. Then the slope automatically calculate 1%. If your culvert is 80, then the cover slope is like the just change. So basically we use the same channel in elevation and the outlet pipe outlet in elevations. Of course, sometimes we maybe not same, but for example, we have a big culvert here. We have a roadway here, whatever. Then we have a big culvert. We have big culvert design, but for downstream, the downstream somehow the below this is called outer elevation. The downstream channel is lower, for example, lower 1 foot. So this called hydraulic drop. This means when the water come out, the hydraulic jump, like the water leaves like this, right? So basically we don't want to design this, but some case we can design if we need. We can design. Basically this is called plunge pools. What's the profile look like, right? Then you get the flow come out and dump in and jump out, then come to the normal. So did not look nice. I just try to look like basically this for example, this flow line. So this this flow, this bottom channel, we get a pool here, and then this is a covered flow come out. Then the hydraulic, the hydraulic, for example, the hydraulic like this, they have a jump. they come out, right? Then they dropped, but they dropped here. They have they have like a large drop. Oh my God, what doing? So basically, this flow, this head water, they call the depths, then come on a jump a little bit, then they jump up, then they come out as normal, right? This hydraulic jump. Then when we design this, we need the sizing the length, based on the outlet, and flow velocity, depth, everything. Right? This is called a plunge pool, or basins. Then when this case, when we design, we have like a, for here the channel maybe like 20, for example, you pull like a 2 foot, you need like a 298, right? That's how a jump there. But normally we don't need. That's the thing. Okay. Then for after the input everything there, we just analyzed. So you come out, come out the water elevation thing, the head water elevation, and the discharge the discharge you put. So if for example the design is 30, go back to that. You go you minimum 10 design 30 and maximum 50, right? And you run. So what happened if you look at here, it's just 10, right? You have head water, right? And you design 30, you get head waters, and if of course 50, you get head waters. That means if you if you input if you input the flow here, you can exactly get the the water level. For example, if you want, I want to see the 2 years 15 water elevations, so head water elevation. So you put a 15, you run, it come out 15. It's a 15, right? Yeah, so except the design, the rest of them, it doesn't matter much. But just like input what you want to look at exactly water elevations. So they can, this is basically the head water elevation we most likely we use for the for the design. Look at the the if overflow or not, right? This is most important parameter. We look at the design flow. We look at the maximum flow if overtopping or not. And of course, we look at the yeah, pipe hydraulic parameters used. For example, you look at the 30s, you get a cover 30, right? Then you come out, the normal depth base normal depth in the culvert, and critical depth. Creek depth is less than what happens if the creek depth is less than normal depth. That means the flow is super critical. That the flow is this is like where simple understand this is the flow is large flow. If this number is small, then this is a sub. That means the velocity is small. That's normal depth water, and the outlet velocity if we design the repair outlet protections, we use with the normal depth and outlet velocity things, right? So that's so if a lower, for example, if we change 500 and change 1 turn, and maybe you get 305. Then you run. Okay, now you see what happens. The overtopping happens. Then you design 50. 100, yeah, design 100. 100 is the overtopping. They show the cover discharge is this much, and the roadway discharge this much, right? If this happened, so when you input when you input this number, you cannot use a constant roadway elevation. You need irregular, and then define define the parameter based on the roadway surface. And yeah, for example, the roadway profile like this, right? So you need to input this with station with the elevations to make sure the embankment of culvert the embankment culvert match the roadway surface. Then they come out exactly the how much overtopping from the road, how much water from the pipe. Yeah, that yeah that's what I have. Yeah. Thank you very much. Yeah.
So, Jerry, thank you very much for a good presentation. You covered a lot of things. Still, we have 8 more minutes. If you guys have any questions, you go ahead and start the question session, please.
Go to your culvert analysis H by 8.
Mhm.
Okay, so now we have 120. Go back to your original discharges, which you have used. Like what were those? Yeah,
Okay.
when you
Oh,
start
yeah. Okay. Okay.
when you
Yeah.
started
Yeah. So
15,
10,
30, and
50,
50.
30, yeah, 50.
Okay, and what is this? Maximum flow is 50. Yeah, and then let's change to diameter to 2 feet. A diameter of the pipe.
2 feet.
Yeah,
2 feet. Okay.
yeah, 2 feet. Okay, let's run it.
No,
You see
it's still overtops.
So it is overtopping. So the whole
overtopping,
point.
not the design. Yeah.
Oh yeah,
Overtopping.
so
Yes.
it is overtopping. Let's change to 2.5 feet.
You know what happened? This called
Diameter.
Yeah, good.
yeah.
Okay.
Now it's good.
So I mean, there are our colleagues from structure as well as from highway department. So what happens is you are showing one table. They are showing the outlet depth, or the inlet depth. So basically, one of the parameter most of the the communities or even SHA or even other clients, when we are designing the culvert, they are looking for the ratio of HW over T. So basically, HW is what's the depth of the water, at the inlet, and the D is the diameter. So they have different criteria. Some people don't allow more than 1.1, more than 1.5. So Jerry, can we calculate HW over D here in this case?
Yeah.
That
This D.
SW over D
Yeah,
sometimes is greater than 2. I forget that it kicks in the small dam checklist.
right. So it is also in there, but at the same time, it is also here because they want you to, but they don't want you to overtop the culvert at just to make sure basically your design is optimum. We cannot have like in initial example when we have 3 feet diameter. So basically, all the design discharges are really, going like an open channel flow. Basically, there was too much space available. So basically, we don't have to, increase the price. So uh, go to the other table, Jerry, please, which have a lot of, yeah, here. So do we have tailwater, outlet velocity, critical depth, flow type, outlet control? So here, inlet. Where is headwater elevation? Yeah. Okay.
Yeah.
Oh, yeah.
Oh, yeah. Yeah.
Yeah. So basically for 30, we have what 3 or 3.17. So we can just see minus 300, right? So basically it's going to be 3.71 divided by 2.5, right?
No. No. The inward is. Let me go back to the. Inward we use is 3.3001. So
No,
that
that's the
means
inlet elevation. So we are looking what is the headwater depth. Basically, there are
yeah,
headwater depth.
that headwater, like for example, you have 301 inward, of course that's 2.7 head depth.
2.71. Okay. And divided by 2.5, so you will get some number, right? So that number has to be for every community. It could be like, they have given the threshold 1.2, 1.1, 1.5, or something like that. And we have to keep it within that limit.
Okay, I think I think we have a deeper. We don't have a deeper. We need, for example,
Yeah.
we ran this one. Well, I think we that's why happened. Yeah.
Yeah.
You
No,
now the 301.
Yeah, that's
Yeah,
good.
yeah.
So
Is
anybody
it?
has any question?
Mm. Yeah, I think you talk about the H over D, the parameter. This for the as Mahendra said, this for the dam safety evaluation tables. Yeah,
Yeah.
that's when this one based on the 100 years, the evaluate the roadway is considered a dam or not. That's a
that that that
different
that
data. That's a
that
different
really
story.
depends. Yeah, that
That's
Yeah.
really
that's
depends.
yeah.
Yeah,
That's
yeah. And then MD is new regulation is every roadway crossing need to be analyzed for that flow chart for the small dam. So that's what
yeah,
we have done in the ICC and Purple Line. All big projects completed that.
yeah.
Whenever we encounter we need to run that flow charts. And other thing, Jerry, can you show me what tailwater we is better in our future project? How we use the tailwater for our engineers' knowledge? So rather than using a fixed tailwater, it's better to give a rating curve. Can you little bit explain on that for our engineers' future knowledge?
You mean the outlet water?
Yeah,
What?
tailwater.
Oh,
How
tailwater.
you plug the
So go,
tailwater
go,
in the
go go to the
H1? What is the
input.
best way?
Go to the input data screen, please.
Yeah, the best way to consider the tailwater for our engineers' knowledge. Because tailwater is a huge factor in this analysis.
Right, based on tailwater control by the downstream channel, right?
So
Downstream channel.
Gary, what are the options we have here? That what he's looking for.
Uh, the downstream.
Yeah, yeah.
Downstream is
Tail. So what
T.
kind of channels we can have?
Basically,
Hmm.
most time we use trapezoid.
It depends, it could be rectangular at certain times, right?
Rectangular we
Well,
no. This is special case. We don't use a rectangular because you see the covered come out the cover, right?
yeah.
Even we have the channel this basic thing, like even the channel is not that much the defined, we still use like a trapezoid channel, because in the
No,
that's right.
that's fine. It depends. I
Mm,
mean, sometimes there may be, rectangular concrete channel.
uh,
Let's go. Then we have irregular channel. Basically, it is like hair cross section, right? So
yeah,
basically,
yeah.
it is not very
You
well
need to
defined. So,
define. Yeah, you need to
yeah,
define the space and the elevation. Yeah, we can. Yeah, this is one used also.
natural channel.
And
And
rating curve, basically, a rating curve is used for the culvert with the manholes. For example, I think in Snap, maybe most of people don't use, but
it is very similar to the irregular channel. So instead of cross section, so we are just entering the data. If
the
this much head depth, we are going to have this much flow. With this much depth, we are going to have this much flow. It is again some sort of irregular, or sometimes it may be for the lakes too.
yeah, basically if you have the large culvert, but they have manholes. So the rating curve, we design this first, then get headwater with the flow, then this area, the headwater of flow of the headwater with the flow is the rating curve on the the upstream culvert.
Yeah, that's very good. You picked
That
up very good example because the headwater of this HY analysis of the downstream culvert would be a tailwater rating for the upstream culvert.
Right. That's a design. Some people just don't care. They just use the same, but that's not
Yeah.
really, yeah. But yeah, this is
Okay.
a design.
So
Yeah.
yeah, that's good enough
No, there
for
is
the
Mahendra, please. There is one more option, Jerry. Let's see what is the tailwater elevation. That's the constant tailwater elevation. Let
yeah
us, yeah. So
yeah.
in this case, if we are discharging the culvert basically into a lake or something like that, and its elevation it is huge, or maybe it is I would say sea or something like that, big lake. So it's a downstream elevation is going to remain the same. And basically, it depends, how much water or the space is available for us. So it has that kind of option too. If you're discharging, your culvert is discharging into a pond, big pond, and the elevation of the pond may be little higher than the invert of the culvert downstream. Basically, it can compute the size of the culvert or the velocity, or how much flow is going to go.
Right.
Yeah.
Right.
Yeah,
Basically,
that's a good information. And other
yeah.
information is for our engineers' purpose. I like to show very quickly. Can you draw a trapezoidal channel? The station 0, elevation this, and station 10, 20. We just go from left to right for the stations and give the elevation of the irregular channel as natural condition. If we plug that gave a best result in my analysis when I did it. So Jerry, can you show that little sketch?
You mean the downstream
Yeah,
cross section? Okay. Yeah.
yeah. So that
Basically,
generally people get confused how to take it. So yeah, very quick, very quick. So on
yeah.
the left
The
side, yeah,
yeah. This
okay,
y this y x. Basically,
yeah,
when we take like a point, you just like oh this point, first point, second
zero,
point,
yeah,
third point. Yeah, this is
and
from
then
the
we give
zero.
a
Yeah,
station and elevation.
yeah,
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 okay,
yes, yeah.
everybody's knowledge. That's good. So let's stop there.
0 and to 12, for example, 20
Yeah,
foot, 0 to 20, and you get a point, and
yeah.
they come out the cross section like this. Yeah.
This is very important in the HYL. Okay, let's do this. Anybody have any question?
Okay, let's go one more time. Jerry, is your file for HIC-HMS is open? HIC-HMS.
Yeah, let me see.
Yeah, if it is open, then we can have little discussion there. This is HIC-HMS.
Oh, he's okay.
Yeah, remember you are
Oh,
showing HIC-HMS.
yeah.
Yeah, you are showing a big watershed. There were three or
Yeah,
four sub
yeah.
watershed.
That's the TC Brown bridge where we calculate.
Yeah, yeah.
Yeah,
So,
that's it.
so I like to have a little discussion on this one. So for our
What
engineers, yeah.
happened?
Yeah.
Oh, we already
Oh,
opened.
the file is gone.
No, no, not the file. Already opened. Yeah,
Oh, okay, okay.
we duplicate open. They don't want to duplicate at the same time. Yeah.
Good, good,
So
good
yeah,
job. Yeah, good job. Here, Jerry, you have done a good job, explaining TR55 methodology, TR55 methodology using curve number and then TR20. And most of our engineers are familiar with the rational formula too. So even if, for our day-to-day work on highway design, where we are designing the culverts or the pipe, basically, rational method may be appropriate. But then we are moving into like half square mile or something like 1 square mile watershed. Probably, depending upon how much budget we have, basically we'll prefer to use TR55 methodology, and it can divide we can have one sub watershed. But sometimes we have really very large watershed. In that case, TR20 has the capability, and Jerry is very familiar with a lot of models. And then HMS has capability too. And the HMS, I think they're trying to convert into the HMS as well as that's hydrology model. HEC-RAS is like RAS is a river analysis system. That's the hydraulic model. Both are basically developed by Army Corps of Engineers, for their floodplain studies or so. But this kind of like Jerry is showing, basically there we have like one, two, three, four sub watershed, right? One, two,
yeah, yeah.
three.
Well, yeah, four. Yeah,
We have
four.
four sub watershed. So in this case, Jerry is using a HMS model. Basically, Jerry and I am working on one big watershed on Vormon's Mill, and that Jerry knows probably that big model covers like 5, 6 major streams, and that's huge HMS model developed by FEMA in 2005. And we are basically we are just reviewing the discharges there. So basically that's covers for the floodplain studies. FEMA prefer these kind of models, and if uh, you know Mike or Tim asked me to do, some sort of, saying that they're going to replace the culvert. So basically, we are going to, use TR55 methodology or something like that. Yeah, this is the, yeah, all the network of the HHS model. So I just wanted to show to the team because they're not familiar with. You can look at it, how many sub watershed we have, how many river streams we have. Basically, so sometimes the water is flowing from one stream to another stream. One is major, the stream, and then basically there are so many watershed which are contributing to this one. So we will try to get projects, once we get those floodplain studies project, which Mahendra and I am working, and we want to have a plan probably, once the way RFP comes or the IDIQ contract comes, you guys will experience these kind of modeling too, with the help of Jerry or me or Mahendra or Anchor. So basically, this is a huge model. So don't be just confined yourself to rational formula or TR55 or HEC-HMS is a huge model. Even it can have for, you know, 2,000 square miles of it. So basically, that we can take care of it. So in this case, you can start the water basically from the very top, and then you can see that how the water are combined. Jerry, can you show where the waters are, the flows are combined in your watershed? The water, yeah, at the outlet, and yes, yeah, here, yeah, you can, yeah, you can just put the, yeah, here, yeah, basically how the water is coming, and basically you can just click on the point where the water from two sub-water sheds are combining, where you are combining the hydrographs at two.
Oh, let me see. For example,
But yeah, 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 yeah,
yeah. For example, you can break
yeah,
a
yeah, yeah, yeah,
three.
yeah,
Okay,
yeah,
okay.
yeah, yeah. And yeah, it is here. And at the same time, TR20 has the capability, when we are modeling the ponds, we have used TR20 in our SHA contract on OED when we were doing some sort of analysis. But HMS is a big model. Basically, you can have a huge dam and you can see that how much flow is attenuating, and it is used. And it is a really big model, and it's integrated with GIS. Basically, Army Corps of Engineers, they started putting together these kind of models probably in late 70s or early 80s, and then basically they keep on going. Now they have uh, that developing HECRAS 2025, which can take care of also the urban drainage system where what we design. So basically, it is improving. It has the good GIS capabilities. HECRAS has the GIS capabilities. We can design the floodplain and all those stuffs. So any questions? I'm really looking forward to see, if a young engineer has any question. And Jerry is very resourceful, in these kind of models. He knows a lot of models, swim model. Even he's very familiar and comfortable with working on the 2D models
Yeah,
too.
I think we are little more. I let Greg ask one question.
Yeah, my question is, from the start of the formula, you use a land use classification. I'm sure that is supposed to be the impervious versus grass versus vegetation runoff rate. But that layer is an aggregate and usually assembled by reflections from imagery. It's really coarse in its resolution. That just seems like right from the beginning, you're skewing your numbers.
Oh, okay. I can answer this question, Jerry. If you would want to add something,
Go ahead. Yeah, no
yeah.
problem. Yeah.
If you want to add something, so
No. That's
basically,
yeah.
yeah. So basically, Greg, so what we are looking at here in the hydrology is not exact science. We are trying to simulate the nature, and nature, I mean, everything looks so good. It seems like that we are assuming, there may be so many little ponds or, puddles and all those stuff, but we still assume that it is very smooth surface or something like that. But in that case, what happens is there is a parameter here, IA. So IA is initial abstraction. So in that aspect, basically, we are accounting for this initial abstraction, which may be the interception by plants. It could be, some little bit storage on little puddles, or it could be something else. So that what is, the whole formula here is we are just, looking at here the IA here, initial abstraction. It is taking care of it. That's number one. Number two, like I said, we're trying to simulate the nature, right? So it is we cannot just it is not we are not designing transistor, like the electrical engineer, or we cannot designing something on the mechanical side. So here we are trying to simulate the nature. So what happens is, the best methodology is when we have these kind of models, uh, FEMA or other regulatory agencies, if available, there is available data, like the stream gauge station or something like that. They want to see that, okay, go back and get the real rainfall data, if we historical data, if it's available, run that model, and I would say route that discharge to all the way to that stream gauging station, and see how far you are from the your simulation and basically the actual discharge observed there. Although somebody could say there may be error in the observation too. So in that aspect, basically what we are trying to do here is basically then we adjust the parameters. In Maryland, Jerry, good job. Here we are trying to see basically these are the the calibration is done with the regression equation. So it gives you the value, one value, the mean value, and then with some standard error, or the standard deviations, of 1 or 2. Basically, it's really approximately 2. It is a plus minus 67%. So within that value, we try to uh, basically see, if our simulated value falls within those numbers. So, Jerry, this is your tier 20, your
Yeah,
hydrologic
basically,
report. Yeah.
yeah,
So,
hydrology.
yeah,
Yeah.
yeah. Do you have that graph which shows that, our simulated value, and it is bounded by the regression
Oh, yeah.
values? No, the
Oh,
graph
yeah,
one.
yeah. Yeah.
Yeah.
Uh, this one.
I think it's in appendix somewhere, in appendix C or something.
Yeah. Yes.
Yeah.
Yeah.
Yeah. Now
You
this
see
is the upper and
the your
lower,
the
but
fingers.
you have the graph for that one too, right?
I have a graph, but this is
Yeah.
appendix. This,
Yeah.
I can open it.
Yeah. I was just reviewing this morning, so basically that one. I, I see that graph basically. I think it is a couple of pages down. Is it Word file or it is a? Yeah. Yeah, this one.
Yeah, this is tier 20, right? This is tier
Yeah.
20 V Pro.
Yeah.
This is
Yeah. So Greg, what is this green line is showing that basically this is our modeling result, and the up and down basically they're showing the regression equation. In this case, basically, if a Maryland hydrology panel has developed and we are using it. So as long as our green line is within this band of blue lines and that orange line, basically we are okay. So basically it is really huge difference. So basically it could be a little bit whatever the charges we have computed. It could be more, it could be less. So basically it is not, there's going to be only one number. So if David Kindle want to use a rational formula, he's going to come with the 200 CFS, and Jerry might come with the 190, and Mahendra might come with the 250 CFS using different methodology, because there is inherent error in every equation there because we're trying to simulate the nature. I hope I answered your question.
Yeah. So, okay, let's do this. We are 16 minute more, so let's not uh, extend this one. Any question, anybody can directly ask or email Jerry, Salim, myself, or Ankur. So, and then other thing, last but not least, all these hydraulics and hydrology HY8 we talked about can also be done by the HydroCAD.
Right.
That we did a presentation last year. I just want to mention that this is another way of doing. The HydroCAD also has that efficiency. So yeah, with that being, I like to conclude our presentation. Any questions? Please let Jerry, Salim, myself, or Ankur. Thank you very much. Thank you, everybody.
Thank you very much,
Also,
Jerry. You did very good
also
presentation, and
very
Thank
you
you.
yeah very
excellent.
use thank you to Jerry.
Yeah.